My name is Sally Joshua, and yeah, I'll be talking about our project, the data warehousing bit of the blockchain secured acoustic signature authentication for military command communication in Swarm intelligence operations. So I'll start with our project overview with the protocol we're designing. It's called, we call it D-AVAP. That's a dynamic attenuation verified protocol. So basically, we are going to discuss the data warehouse requirements of this protocol, and then we shall go ahead and look at the implementation bit. So it's a system designed to ingest and analyze multi-source data from acoustic sensors, blockchain ledgers, and drone telemetry. That's basically data from Swarm agents in Swarm intelligence. Yeah, and we chose to use the Galaxy schema for this. Particularly, we have a sample dashboard here, which we have talked about in a separate video that you can find on my channel. Yeah. So the related works, we got ideas from some of this work, and the first one is Acoustic Vision Pro, and this is an open source platform for room impulse response analysis and acoustic characterization. And yeah, so it had many physics-based acoustic metrics for environmental verification, transmission quality monitoring, and perceptual quality assessment. Yeah, and some of these, there were very many, but these are the ones that we found interesting that we could borrow. Yeah, so this is the kind of data we would have to store. We have the reverberation time and early decay time. Yeah, so with the reverberation time, we can be able to detect and estimate the environment in which that audio was recorded. For example, if someone records an audio from an enclosed room or an empty room, that wouldn't be the same. It wouldn't have the same reverberation time as an audio that has been recorded in the field. Yeah, in a war, during war. Then we have the energy decay curve and direct to reverberant pressure. Yeah, these monitor anomalies like noise, flows, truncation, or repositioning during multiple transmission. Yeah, it's a bit more similar to the previous one. That's the reverberation time and early decay time. Then we have the clarity indices. This helps us to check for quality degradation from re-encoding and compression. Every time these audios are shared between Swarm agents, the quality drops. So this metric helps us understand, helps us to measure that and see how we can deal with it. Then we have the spectral stability. And this detects frequency imbalances or clipping artifacts in propagated audio. And then the speech transmission index and signal to noise ratio. That quantifies speech quality preservation for content-specific evaluation. And then this was a journal. It's called Potential of Swarm Intelligence in Big Data Analytics. So this paper mainly talks about how Swarm agents can be used in big data analytics without having to use a central server to analyze all the data. So this can be done in the following steps. The first step would be to extract features. Each agent can extract traits from the video, such as speech, rhythm, noise, and other metrics that we have talked about. And then it will have to analyze these features independently. And then for step 3, in case there are variations, like each Swarm agent has analyzed the feature in its own way, then we shall need to carry out a majority voting to decide which variation we are going with. Yeah, and then from here, the data can be sent to the server so that it can be accessed remotely by any other interested party. Yeah, so normally, all this data is sent to the server and analyzed. The server is one that does the analytics, or it's done manually, and then that's how the analytics are generated. But for us, in this case, we are looking at this paper proposes doing the analysis using the Swarm agents themselves. And then another paper is the deployment of an IoT system for adaptive in-situ soundscape augmentation. So this paper, it's mainly about an IoT system, but what we are really interested in this paper is the soundscape augmentation and the real-time noise optimization. Yeah, so context-aware soundscape modeling. This basically uses acoustic metrics and perceptual context awareness to optimize noise handling, which can ensure that audio is validated against its expected environment before pattern analysis begins. Yes, this is just what I said earlier. We want to ensure that the audio has been recorded from the right environment. You wouldn't expect an audio recorded from a battlefield to be the same as an audio file recorded from a studio. So we'd be able to detect that using some of the techniques discussed in this paper. Then adaptive real-time augmentation. Yeah. So basically this looks at masking profiles and gaining levels automatically, adjusting to environmental changes. For example, if someone records an audio in the field and it's raining, and then they also record an audio when it's sunny, we have to deal with those environmental changes. So that's what this paper also talks about. We need to find a way to deal with those environmental changes of when someone records an audio in each of those different scenarios. When someone records an audio and they are firing a gun next to him or her. Yeah. Then the distributed Swarm feedback and refinement. Agents share quality metrics and environmental fingerprints, which enable cooperative optimization while maintaining feature integrity for reliable pattern recognition. Yeah, so that's basically it. Then another paper is a decentralized retrieval augmented generation system with source reliability secured on the blockchain. Yeah, so in this paper, it talks about decentralizing a RAG architecture, and it secures all this and ensuring reliability and integrity. So some of the concepts that we also borrowed from this paper is the blockchain secured reliability and smart contracts. So this, if we are to implement this, it will help with ensuring that all executed Swarm commands are immutably logged and consensus validated before acceptance. Yeah, so that in case someone wants to know what happened, maybe the Swarm misbehaved or it didn't do something well, someone can go back in the logs and see what really happened. And the logs cannot be mutated, they cannot be deleted. Yeah, you can only append to them. You can't delete or do anything with them. Yeah, that's that. Then the digital signature verification. So as as you must have known earlier, we said we would have a quorum of, I think, 75%. So we want to be sure that it's only SWAM agents, the agents in the SWAM, that are actually participating in this vote. It's possible one attacker might be able to compromise the system, might be able to engage, or might have a false agent, and then they might overload, they might falsify some of these votes to get the SWAM to carry out a wrong command. So here we would have to verify each SWAM using public and private keys. Yeah, that's encryption. Yeah. Then consensus-driven updates. Yeah, that's the quorum I just talked about, the 75% quorum. Yeah, then peer-to-peer validation and majority honest assumption. Yeah, so the peer-to-peer validation is what I've just said. We shall need to use the asynchronous, that public and private key encryption to ensure that each SWAM agent is verified that it's actually a member and it's supposed to be participating. Yeah, so our problem statement. So the lack of a unified system to integrate and analyze disparate data from acoustic sensors, blockchain ledgers, and drone telemetry. Yeah, because with our project, we are trying to eliminate the use of having a central data location or central data storage, which can be compromised and attackers can have access to everything or can do anything. So we are trying to find a way to do all this, yeah, in a decentralized way. And yeah, so here we're going to talk about the schema we have chosen, and we're going to talk about the schemas we haven't chosen and why we haven't chosen them. So the purpose and objectives: to integrate diverse data streams and optimize the data optimize with data structures, yeah, and enable advanced visualization, and then also provide accessible interaction. Yeah, so the first schema I'll talk about is the star schema and why it was rejected. So the star schema, basically, it has a central table, which can be the main table, and then it has dimensions which spread out from the main table. For example, if this can be a sales table, and then you can have the time, you can have the sales that were made, you can have sales that were made based on promotions, you can have sales that were made to specific customers. Let's say a customer is a wholesaler, is a wholesaler, or it's a retail shop. You will have all this separated as sub-dimensions of the main table, as dimensions of the main table. So it doesn't clearly reflect the business relationships, and in the D-AVAP, it would struggle with the complex structure of the relationships between the acoustic signatures and the blockchain transactions. We would need to have two separate star schemas to represent that, and that's not feasible. Yeah, and then the snowflake schema and why it was rejected. It's an extension of the star schema. As you can see, we have one fact table, and then we have dimension tables extending from that fact table. So at the dimension table level, this makes it a star schema. But what makes it a snowflake is when those dimension tables also have some sub-dimensional tables. Yeah, so that's what make it a snowflake schema. So yeah, for this one, it requires real-time information sharing and retrieval, and this schema was not chosen because it would be too slow due to normalization requiring more joins that would increase the query latency. Yeah, and also, as I said earlier, we would need to have two snowflake schemas to bring out a relationship between the acoustic signatures and the blockchain logs. Yeah, and then we have the hierarchical schema and why it was rejected. So the hierarchical schema basically represents hierarchy relationships. For example, as you can see here on the side, we have a company. Let's say we have a database of companies. Now we would have a table that has a list of all the companies, and then you would need to have another table that shows the departments in each of those companies, and then you would have to go ahead to demonstrate the offices in each of those departments. Now that's a hierarchical schema. It's the best schema to use when you want to capture relationships between, not relationships, like hierarchies. If you want to capture hierarchies, for example, if you want to capture, let's say, employees, you can have a CEO, and then you have the CTO, then you have the senior developer, then the developers, then you have the interns. So such relationships are best for a hierarchical schema. And it's the best when you're working with JSON files, XML files.
Hello everyone, I'm Shamhenda Sumaya, and I'll be taking you through a few of the other schemas that we evaluated and rejected, and I'll be giving you reasons why we rejected these ones I'm going to talk about. Starting with a network schema. This is just like an extension of the hierarchical schema that my colleague has just taken you through. And well, here we have like the children and parents. They have like a bi-directional relationship, meaning that filtering flows like in all directions or in both directions. And for this model, like the records serve as nodes, and the explicit links, they represent relationships between them. And well, for every record, it is physically linked to the others using pointers, as you can see in this diagram we have here. And in our project, in case of a drone status changes rapidly or a blockchain transaction fails, updating these complex links creates a computational burden, making this schema really non-scalable and not suitable for our project. Well, we'll move on to the next one, the physical schema and why it was rejected. Well, we evaluated this one also, and this schema surely focuses on how data is stored in the actual hardware. And our project really is a software protocol. So we are using the existing hardware, such as the drones. We don't have to design or restructure the structure of the hardware, like restructure the structure of drones. We don't have to do that. And this is why this is not feasible and it is not applicable for our project. Well, moving on to the logical schema. Again, we evaluated this one also, and we saw that it is suitable like for illustrating a particular domain within an organization. It is commonly used when trying to like have a deep understanding about a business process, how it operates. And well, in our project, we are using like acoustic features, which are extracted and stored and verified. So there's nothing like that where we need to like understand a business process. And this schema can only be used to implement like a specific business process, but not the entire data requirements of the system. That is why it was rejected. And also here we have an illustration of how it flows. Well, for the interest of time, let's move on to the conceptual schema and why it was rejected. Well, in this model schema, it gives like a bird's eye view of the data requirements of the business, and this is then used like to dig deeper and find sub relationships that may have not been captured. And well, according to our project, this is mainly used. Our project is mainly used to have an overview of the data requirements of the protocol, and then one has to go like deep and find the relationships between the entities which aren't explicit in this schema. That is why this schema was rejected. And moving on to the flat schema and why it was rejected. Well, this has many names. It's called the flat schema or the big table or the white table schema also. And here this one uses like a single table having multiple fields. As you can see here, we have this table that has multiple fields, the ID, name, email, phone. But this table, this schema leads to like redundancy when used in our project, and also leads to like memory wastage. And
Hello, I'm Henry Kishami, and moving on to the schema that we've chosen for the project, it's the Galaxy schema. The Galaxy schema has multiple fact tables, which represent different processes, but they have common dimension tables. In this case, following the illustration on the right, you can see that there are two dimensional tables in common, but you also have, for each fact table, you have different dimension tables. And this, as it looks like, offers more flexibility than the star and the snowflake schemas, and which is the reason why we went with the Galaxy schema. We want a real-time analytics dashboard that's going to give us real-time insights. And the only way we can do this is if we split the data that we want to visualize in two fact tables, because they don't even have to be joined, because they don't have relationships, if I would say, between them. And one of them is going to be the authentication events fact table, and the other fact table is going to be the system telemetry. The system telemetry has CPUs, locations, latencies, and for the authentication events, we have however many number of commands have been successfully executed, and so on. So those two fact tables will have common dimension tables such as time, agent, that is for the Swarm agent, and for the commander, different details about the commander and what they are doing in our system. And so with that, we can show the methodology we are planning for the Galaxy schema comes from in step 2. But let's start from step 1. Step 1, we want to ingest real data. That will be coming from sensor logs, from sensors hosted on our IoT devices. And at the same time, we also want to be getting in blockchain transactions as they come in, and the drone data, that is battery, maybe CPU, latency I've just mentioned. All those raw data is going to come in, and step 2 is where the data warehouse really comes in. And this is where we are going to do the process of ETL, which is common to all data warehouses. That is, we extract, we transform, and then we load our data. I've already explained this is where the Galaxy schema is going to come in with much more flexibility, if I would say, having two fact tables. So we won't be doing more joins than necessary because we want this to be happening in real time. Now, before we visualize this data, this structured data that we've just cleaned and transformed, we want to be able to store it somewhere in a repository so that it can be used maybe at a later stage, maybe for auditing purposes, or maybe for us trying to maybe visualize or maybe train a machine learning algorithm on top of that. This is where we're going to store our data. And then from there, now we can do our visualization, where we're going to be showing a real-time map of all the threats, where they're happening from in perspective of the commander. And we're also going to be showing the latency. The latency is around how those SWAM agents are doing their operations. And also we want to show the successful commands that are being executed. This is common to the commander's insights dashboard, so to say. And these are the references of all the reviewed papers, the 4 papers we reviewed. And with this, I say thank you for watching us, and stay tuned for more.